The Artemis 2 crew have just looped around the moon aboard the Orion spacecraft. They did not land. They did not step outside. They swung past a world with no air, no magnetic shield, and surface temperatures that swing from 250 degrees above zero to nearly 300 below. Radiation sleets through the regolith. Dust sharper than shattered glass coats everything it touches. By every intuitive measure, the moon is a dead end. Yet NASA just committed $20 billion to build a permanent base there. And the reason is not sentimentality. The reason is math. When you compare every destination humans could actually reach, resupply, and rescue, the moon is not the friendliest option. It is the least impossible one. And that difference may change everything. If you enjoy stories that challenge what you think you know about our future in space, consider tapping that like button and subscribing. It genuinely helps me keep making these deep dives for you. Now, settle in and get yourself comfortable. Let's begin. Step outside without a spacesuit on the moon, and you will be dead in roughly 90 seconds. Not from the cold, although the cold is savage. Not from the radiation, although the radiation is relentless. You will die because there is no air. None. Not a thin atmosphere. Not a wisp of oxygen clinging to crater rims. The moon has a surface pressure roughly 300 trillion times lower than what you experience sitting in your chair right now. Physicists do not even call it an atmosphere. They call it an exosphere, a scattering of atoms so sparse that individual molecules travel for miles before encountering another particle. At sea level on Earth, every cubic centimetre of air contains roughly 25 quintillion molecules bouncing off each other in constant chaos. On the moon, that same volume holds perhaps tens of thousands of molecules at night, dropping even lower during the day, mostly helium, neon, and argon, released by radioactive decay and solar wind interactions. The difference is not incremental, it is absolute. Earth's atmosphere is a warm blanket wrapped around every living thing on the planet, regulating temperature, blocking radiation, carrying sound, delivering oxygen to every breath you take. The moon has nothing. The moment your skin contacts raw lunar vacuum, dissolved gases in your blood begin forming bubbles. Your saliva boils on your tongue, not because the temperature is high, but because the pressure is so low that water transitions directly into vapor at body temperature. Your lungs, accustomed to pushing against atmospheric pressure, would rupture if you held your breath. Your eardrums would burst. Consciousness fades within 15 seconds as oxygen-starved blood reaches the brain. And this is merely the first of many ways the moon tries to kill you. The thermal environment is equally merciless. The moon rotates once every 29.5 Earth days, creating a day-night cycle that stretches each phase to roughly 14 Earth days. During the lunar day, surface temperatures at the equator climb to approximately 127 degrees Celsius, hot enough to boil water if water could exist in liquid form there, which it cannot. During the 14-day night, temperatures plummet to approximately minus 173 degrees Celsius. That is colder than any naturally occurring temperature ever recorded on Earth's surface. Colder than the South Pole in the depths of Antarctic winter. Colder than liquid nitrogen. The swing from peak day to peak night spans roughly 300 degrees Celsius. Nothing on Earth prepares you for this thermal violence. On our planet, the atmosphere acts as a thermal buffer, redistributing heat through convection and holding warmth against the surface through the greenhouse effect. Weather systems transport energy from the equator toward the poles. Oceans absorb and release heat over long cycles. The result is that even the most extreme earthly temperature difference between the hottest desert and the coldest polar night amounts to roughly 150 degrees Celsius. The moon doubles that range across a single day-night cycle at the equator, and it does so with no buffer, no transition, no gradual twilight. The terminator line, where day meets night, is knife-sharp. Step from sunlight into shadow, and the temperature drops catastrophically within meters. For any habitat, this thermal regime creates engineering nightmares. Materials expand in the heat and contract in the cold. Seals, joints, and connectors fatigue under repeated thermal cycling. Electronics designed for Earth's mild temperature range fail, overheat, or freeze. Apollo hardware was engineered for missions lasting only hours to a few days on the surface. Even within that narrow window, thermal management consumed enormous engineering effort. Every Apollo lunar module carried coolant systems, insulation blankets, and reflective coatings to survive the temperature extremes. Extending surface operations to weeks or months multiplies these challenges by orders of magnitude, because every additional thermal cycle stresses materials closer to failure. But the thermal environment is almost manageable compared to what comes next. Radiation on the moon is a slow and invisible killer. Earth's magnetic field deflects the vast majority of charged particles streaming from the sun and from deep space. This magnetosphere acts as an enormous shield, bending solar wind protons, alpha particles, and heavier ions around the planet, channeling them toward the poles where they produce auroras rather than biological damage. Behind this magnetic shield, Earth's atmosphere provides a second layer of protection, absorbing most of the remaining high-energy particles and ultraviolet radiation before they reach the surface. The Moon has neither defense. Its global magnetic field, once roughly twice as strong as Earth's current field, weakened over billions of years as the Moon's small iron core gradually cooled and crystallized, with the dynamo that generated the field shutting down approximately 1 billion years ago. Without that field, the lunar surface now lies fully exposed to the solar wind, a constant stream of charged particles flowing outward from the sun at speeds exceeding 1 million miles per hour. During calm solar conditions, this bombardment is steady and damaging. During solar particle events, when the sun erupts with coronal mass ejections or solar flares, the radiation dose spikes to levels that can deliver a lethal exposure in hours. Galactic cosmic rays present an even more insidious threat. These particles originate from supernova explosions and other violent events scattered across the galaxy. They travel at nearly the speed of light and carry enormous energy. Unlike solar particles, which are mostly protons and alpha particles that can be partially blocked by moderate shielding, galactic cosmic rays include heavy ions, iron nuclei, carbon nuclei, oxygen nuclei that punch through centimeters of aluminum shielding like bullets through paper. When these heavy ions strike biological tissue, they shatter DNA strands and produce cascades of secondary particles that amplify the damage. NASA's current estimates suggest that an astronaut spending 1 year on the lunar surface with minimal shielding would accumulate a radiation dose of roughly 400 millisieverts. For context, the average person on Earth receives about 3 millisieverts per year from natural background radiation. 400 millisieverts represents a statistically significant increase in lifetime cancer risk. During a major solar particle event, an unshielded astronaut could receive a dose exceeding 1 sievert within hours, causing acute radiation sickness including nausea, immune suppression, and organ damage. A dose of 5 sieverts or more is typically fatal within weeks. Apollo astronauts accepted these risks because their surface stays lasted only hours. The longest Apollo surface mission, Apollo 17, kept astronauts Eugene Cernan and Harrison Schmitt on the Moon for approximately 75 hours. Their total radiation exposure for the entire mission, including transit, remained within acceptable limits, precisely because the exposure window was so short. Extending that window to weeks or months fundamentally changes the radiation calculus. What was an acceptable short-term risk becomes a cumulative long-term hazard that demands either massive shielding or underground habitation. And then there is the dust. Lunar regolith is not like any dust you have encountered on Earth. On our planet, wind and water erode rock fragments into smooth, rounded particles over millions of years. Atmospheric weathering softens edges. Chemical processes alter mineral surfaces. The result is the relatively benign dust and sand we experience daily, particles that irritate but rarely injure. On the Moon, there is no wind. there is no water. There is no chemical weathering. Instead, the lunar surface has been pulverized for over 4 billion years by micrometeorite impacts, each collision shattering rock into progressively finer fragments without ever smoothing the edges. The resulting particles are jagged, angular, and sharp at microscopic scales. Many grains resemble tiny shards of broken glass. Some are coated with a thin layer of vapor-deposited iron created by the intense heat of micrometeorite impacts, making them chemically reactive and electrostatically charged. Apollo astronauts discovered the dangers of lunar dust firsthand. Despite rigorous decontamination procedures, dust infiltrated every system it contacted. It abraded spacesuit visors, reducing visibility. It jammed zippers and degraded suit joints. It clogged equipment seals. It coated optical instruments. When astronauts returned to the lunar module and repressurized the cabin, fine dust particles became airborne and were immediately inhaled. Harrison Schmitt, the geologist astronaut on Apollo 17, reported symptoms resembling hay fever after breathing lunar dust inside the lunar module. His throat became congested. His eyes watered. Other astronauts reported similar irritation. These symptoms appeared after exposure lasting only hours. What the Apollo crews described about lunar dust went beyond clinical symptoms. When Gene Cernan and Harrison Schmitt repressurized the lunar module after their final moonwalk on Apollo 17, the cabin filled with a smell that both astronauts found immediately distinctive and deeply unsettling. Schmitt described it as resembling spent gunpowder. Cernan compared it to the acrid residue left after a firearm discharge. Other Apollo crews reported similar impressions, a sharp, burnt metallic odor that permeated the cabin within minutes of removing their helmets. The smell was not imagined. Researchers later determined that it likely resulted from the oxidation of highly reactive iron nanoparticles and fractured mineral surfaces on the dust grains. In the lunar vacuum, these surfaces remain chemically virgin, never having encountered oxygen or moisture. The moment they contact a pressurized, humid cabin atmosphere, they undergo rapid oxidation, releasing volatile compounds that the human nose registers as burning or metallic. You are literally smelling rocks reacting with air for the first time in billions of years. The smell was more than an unpleasant footnote. It signaled a chemical reactivity that made lunar dust fundamentally different from any terrestrial dust hazard. Industrial hygienists on Earth deal with silica dust, coal dust, asbestos fibers, all of which are dangerous but chemically stable. They have been weathered, tumbled, and oxidized over millennia. Lunar dust grains carry pristine fracture surfaces that have never been chemically neutralized. When these surfaces contact moist tissue, the lining of the nose, the surface of the eyes, the delicate alveoli deep in the lungs, they may trigger oxidative reactions directly in biological tissue, generating free radicals that damage cells at the molecular level. Laboratory studies using simulated lunar dust have demonstrated cytotoxic effects on human lung cells, including inflammation markers and DNA damage, at exposure concentrations well below those that Apollo astronauts encountered in their cabins. Cernan documented another dimension of the dust problem that rarely appears in engineering assessments: its effect on vision. Spatial awareness. Lunar dust coated his visor within hours of surface activity, degrading optical clarity with a fine film that could not be fully removed by wiping. The electrostatic charge on the particles caused them to adhere to any surface they contacted, including the polycarbonate visors that represented the astronaut's only visual interface with the external environment. Cernan reported that by the third EVA, his visor had accumulated enough microabrasion from dust contact and cleaning attempts that visibility was noticeably reduced. For a 3-day mission, this was a manageable nuisance. For a 3-month stay involving daily EVA activity, cumulative visor degradation becomes an operational hazard. Replacement visors can be shipped from Earth, but the fundamental problem remains. Every interaction with the exterior environment brings dust into contact with equipment that must remain optically, mechanically, and electrically functional. Beyond the physical hazards, Apollo astronauts encountered a psychological environment that no training simulation on Earth could fully replicate. The moon is silent. Not quiet in the way a remote desert is quiet, where wind still whispers and distant animals occasionally call. Silent in an absolute sense that human beings have never evolved to experience. Sound requires a medium air, water, solid material to propagate. On the lunar surface, the only sound an astronaut hears is the hum of their own life support system, the rasp of their own breathing, and the faint mechanical noises transmitted through their suit structure when they move. Step outside the suit, and there would be no sound at all. A boulder could crash into the surface 50 meters away, and you would feel the vibration through the ground but hear nothing. The psychological effect of this silence is difficult to overstate. Humans are acoustic animals. We monitor our environment continuously through sound, even during sleep. We orient ourselves, detect threats, and maintain awareness of our surroundings partly through auditory processing. On the moon, that entire sensory channel is amputated. The world beyond the visor is a silent movie played at full brightness and absolute contrast. The visual environment reinforces the alienness. Earth's atmosphere scatters light, creating the blue sky, the gradient of sunrise and sunset, the soft diffusion of shadows, and the haze that provides depth cues at distance. On the moon, there is no scattering. The sky is black at all times, even at local noon with the sun blazing overhead. Shadows are knife-edged and absolute, not the soft penumbra of terrestrial shade, but hard geometric cutouts of total darkness adjacent to blinding illumination. An astronaut walking on the surface sees objects in direct sunlight rendered in stark, almost overexposed clarity, while anything in shadow becomes nearly invisible. Depth perception suffers badly because the atmospheric cues that human vision relies upon to judge distance simply do not exist. Alan Bean of Apollo 12 reported difficulty estimating how far away objects were on the lunar surface. Craters that appeared to be a short walk away turned out to be much farther. Equipment left at the landing site seemed to shrink and disappear, with distance faster than expected. The horizon, on a body with roughly 1/4 Earth's diameter, curves noticeably closer. On flat terrain near the equator, the lunar horizon sits only about 2.5 kilometers away compared to nearly 5 kilometers on Earth. The world feels small, closed in, and hemmed by a blackness that begins immediately at the ground line and extends in every direction to infinity. Several Apollo astronauts described a visceral sense of wrongness about the environment that persisted throughout their surface stays. Buzz Aldrin famously called the lunar landscape magnificent desolation. The phrase captured something precise, a world that was visually striking and simultaneously fundamentally inhospitable at a level that registered not just intellectually but physically in the gut. The wrongness came from every sensory channel simultaneously. The gravity was off, movements felt floaty and imprecise, requiring constant conscious adjustment. The light was off too harsh, too contrasty, no colour in the sky. The sound was off none at all except your own body. The horizon was off too close, too sharp, dropping away into blackness. The ground was off a fine powder that behaved like wet sand in some conditions and talcum powder in others, clinging to everything with electrostatic tenacity. Human beings can adapt to remarkable conditions given time, and Apollo astronauts reported growing somewhat more comfortable with each EVA, but they also reported that the alien quality of the environment never fully receded. It lurked beneath the focus of task execution, surfacing during pauses, during moments of quiet between activities, during the long hours inside the lunar module waiting for the next EVA window. For missions lasting days, this background dissonance was tolerable. Whether it remains tolerable for months or years is a question no one can answer from data, because no one has tried. The psychological cost of sustained habitation in an environment that triggers continuous low-grade sensory wrongness represents an unknown risk factor that sits alongside radiation, dust, and thermal cycling in the ledger of lunar hazards. It cannot be engineered away with better habitat design, only mitigated through careful crew selection, psychological support, meaningful work, and the communication lifeline to Earth that proximity preserves. All of this, the gunpowder smell, the visor abrasion, the silence, the visual alienness, the instinctive sense that everything about this world is fundamentally wrong, describes an environment that no rational analysis would select as humanity's next home. And yet here we are, planning exactly that. The full toxicological profile of lunar dust remains incompletely understood, but laboratory studies using simulated lunar regolith suggest that prolonged inhalation could cause serious respiratory damage. The sharp, glassy particles can penetrate deep into lung tissue, and the reactive iron coatings may trigger inflammatory responses similar to those caused by asbestos or silica dust on Earth. Some researchers have described the potential condition as lunar silicosis, a chronic lung disease that could develop over months or years of repeated exposure. For any sustained human presence, dust management becomes not merely an engineering challenge but a medical imperative. Every airlock cycle risks introducing particles into habitable spaces. Every surface excursion grinds dust into suit components. Every piece of equipment returned from the surface carries contamination that must be contained, filtered, or eliminated before it enters breathable air. Apollo missions could tolerate dust infiltration because the crews were leaving within days. A permanent presence cannot afford that luxury. Micrometeorites add another layer of danger that most people never consider. Earth's atmosphere burns up roughly 100 tons of cosmic debris every day, the shooting stars you see on clear nights. These particles, some as small as grains of sand, enter the atmosphere at speeds exceeding 40,000 miles per hour and vaporize from friction long before reaching the ground. The atmosphere provides a free, perpetual shield against this constant bombardment. The Moon has no such shield. Every micrometeorite that approaches the surface arrives at full velocity and impacts without deceleration. Particles smaller than a millimeter strike the surface thousands of times per day across the Moon's total area. Larger particles arrive less frequently, but carry devastating kinetic energy. A particle the size of a grain of rice traveling at 50,000 miles per hour packs enough energy to puncture aluminum shielding used on spacecraft. A pebble-sized fragment could breach a habitat wall. The probability of a direct hit on any single habitat module during a short mission is extremely low, but sustained presence changes probability into near certainty over time. A base operating for decades faces cumulative exposure to billions of micrometeorite events across the surrounding surface. Shielding strategies exist, including burying habitats under regolith, but each solution introduces new engineering requirements and mass penalties that complicate construction. The Moon also lacks another feature we take entirely for granted: a stable gravitational environment suited to the human body. Lunar gravity measures roughly 1/6 of Earth's gravity. This means an astronaut weighing 180 pounds on Earth weighs only 30 pounds on the Moon. Walking feels like bouncing. Lifting heavy objects requires almost no effort. This sounds liberating, even fun. Apollo footage of astronauts hopping across the surface makes low gravity look like a playground. The physiological reality is far less charming. The human body evolved over millions of years under Earth's gravitational load. Our bones maintain their density because gravity constantly stresses them, triggering cellular processes that deposit calcium and reinforce skeletal structure. Our muscles maintain their mass because gravity demands constant exertion just to stand upright, walk, and move. Our cardiovascular system regulates blood pressure based on gravitational expectations, pumping harder to push blood upward from the legs to the brain. Remove that gravitational load, as occurs in the microgravity of the International Space Station, and the body begins deteriorating within days. Bones lose calcium at roughly 1 to 2% per month. Muscles atrophy. Cardiovascular fitness declines. Fluid shifts toward the head, increasing intracranial pressure and potentially damaging vision. Astronauts returning from 6-month stays on the space station require weeks of rehabilitation to walk normally. Lunar gravity at 1/6 Earth normal represents an intermediate case that scientists have never studied in. humans for extended periods. No human has ever lived under lunar gravity for longer than 3 days. Whether 1/6 gravity is sufficient to prevent the bone loss and muscle atrophy seen in microgravity remains genuinely unknown. Some researchers suspect it may slow the rate of degradation compared to zero gravity, but not eliminate it entirely. Others argue that even partial gravity may be enough to maintain basic musculoskeletal function if combined with exercise protocols. The honest answer is that nobody knows, and the only way to find out is to send people there for extended stays and monitor what happens to their bodies. That uncertainty itself represents a risk. Consider what all of this means when assembled into a single picture. The moon offers no air, no atmospheric pressure, no protection from radiation, no thermal regulation, no defense against micrometeorites, gravity that may slowly destroy human bones, and dust that could shred human lungs. Every system required for survival must be engineered, delivered, and maintained artificially. Air must be manufactured or extracted and recycled with near-perfect efficiency. Water must be recovered from every source and purified endlessly. Temperature must be actively regulated across a 300-degree range. Radiation must be blocked by mass shielding. Dust must be managed at every interface between interior and exterior environments. Food must be grown, shipped, or stored in quantities sufficient for crews that cannot be evacuated quickly. A failure in any single life support system can kill everyone in the habitat within hours. A pressure breach, a cooling system malfunction, a carbon dioxide scrubber failure, a contaminated water supply. Each scenario represents a lethal emergency with no hospital, no fire department, no emergency services, and no breathable atmosphere waiting outside the door. On the International Space Station, astronauts facing catastrophic failure can theoretically board a Soyuz or Crew Dragon capsule and return to Earth within hours. On the Moon, evacuation requires days at minimum, assuming a return vehicle is fueled, functional, and available. Apollo 13 demonstrated what a single equipment failure means in deep space. An oxygen tank explosion crippled the command module during transit to the Moon, forcing the crew to use the lunar module as a lifeboat. The astronauts survived through improvisation, endurance, and an extraordinary ground support effort that worked around the clock. They returned to Earth after 4 harrowing days. On the lunar surface, an equivalent failure would leave a crew stranded 240,000 miles from the nearest hospital, breathing recycled air, rationing water, waiting for a rescue that might take days to arrive or might not arrive at all. Nothing about this picture suggests that the Moon is a welcoming place. Nothing about the thermal environment, the radiation flux, the dust chemistry, the vacuum, or the gravitational deficit makes the Moon resemble anything humans would voluntarily choose as a home. The Apollo program proved that humans can visit the Moon, survive brief excursions on its surface, conduct science, plant flags, collect rocks, and return alive. But visiting and living are separated by an enormous gulf. Visiting means tolerating a hostile environment for days while relying on supplies brought from Earth. Living means creating a self-sustaining, or at least regularly sustained human presence that endures across months and years. Surviving not just the known hazards but the unknown failures that inevitably arise when complex systems operate in extreme environments over long durations. The International Space Station, operating in low Earth orbit, just 250 miles above the surface, has taught us how difficult sustained human presence in space truly is. Despite being close enough to resupply every few weeks, despite operating in relatively shielded conditions inside Earth's magnetosphere, despite 25 years of continuous occupation and iterative improvement, the station still experiences regular equipment failures, air leaks, cooling malfunctions, and supply chain challenges. Crews spend enormous fractions of their time on maintenance rather than science. The station requires constant logistical support from multiple space agencies and commercial providers. The Moon is 1,000 times harder. It is 1,000 times farther from help. It offers 1,000 times less margin for error. And yet, Despite all of this, despite the vacuum and the radiation and the dust and the thermal violence and the bone-wasting gravity and the micrometeorite rain, the Moon remains the single most serious candidate for humanity's first sustained home beyond Earth. That statement sounds almost absurd after everything we have just described. How can the most hostile environment humans have ever visited also be the most realistic place to build a permanent presence? How can a world that tried to kill every Apollo astronaut within hours of arrival be the same world where engineers are now planning habitats designed to shelter crews for months? The answer is not that the Moon has become less dangerous. It has not. Every hazard described in the last several minutes remains exactly as lethal today as it was when Buzz Aldrin stepped onto the Sea of Tranquility in 1969. The regolith is just as sharp, the vacuum is just as absolute, the radiation is just as relentless. Nothing about the Moon has changed. What changed is our understanding of the alternatives. For decades, the popular imagination placed Mars at the center of humanity's spacefaring future. Mars has a thin atmosphere. Mars has water ice. Mars has a day length almost identical to Earth's. Mars has seasons, polar caps, ancient river valleys, and a romantic mystique that the Moon with its grey desolation has never matched. Science fiction built entire civilizations on Mars. Public enthusiasm rallied around Mars. Mission architectures targeted Mars as the ultimate destination for human exploration. But as engineers began seriously calculating what sustained human presence on Mars would require, the numbers told a different story. A story not of impossibility, but of staggering logistical difficulty that dwarfs the already enormous challenges of the Moon. The Moon is savage, yes. The Moon is hostile, yes. But the Moon has one advantage so powerful that it reshapes the entire equation of human survival beyond Earth. That advantage is not comfort, it is not hospitality, it is not resources, although resources matter and we will explore them soon. The advantage is something far simpler, far more fundamental, and far more consequential than any single environmental feature. The advantage is proximity. The Moon is close. Extraordinarily, almost absurdly close by the standards of space. And that closeness changes everything about whether humans can realistically learn to survive there. Not because closeness makes the Moon safe. It does not. But because closeness makes failure recoverable. It makes mistakes correctable. It makes rescue conceivable. It makes resupply routine rather than heroic. It makes the difference between a single desperate expedition and a sustained iterative presence that can grow, adapt, learn, and endure. What comes next reveals exactly how much that closeness matters, and why it transforms the Moon from a dead-end wasteland into the most realistic first chapter of human life beyond Earth. 240,000 miles. That is the average distance between Earth and the Moon. Written out, it looks modest next to the numbers astronomers usually throw around. It is not billions, it is not trillions. It is a number a human mind can hold without collapsing into abstraction. And yet 240,000 miles is still incomprehensibly far by any earthly standard. It is roughly the distance you would cover if you drove a car around Earth's equator 9.5 times without stopping. If you walked at a steady pace, day and night, the journey would take roughly 83 years. No human has ever travelled that far on foot, and no human ever will. But in space, 240,000 miles is practically next door. Light crosses that distance in 1.3 seconds. A radio signal sent from the lunar surface reaches mission control in Houston before a person can finish blinking. A distress call, a telemetry alert, a medical emergency report, any of these arrive on Earth essentially in real time. A flight surgeon on Earth can monitor an astronaut's heart rate on the Moon with barely more delay than monitoring a patient in the next room. Conversations happen naturally, with pauses so short they feel like ordinary phone lag rather than interplanetary distance. This might sound like a small technical detail, a footnote in the engineering specifications of lunar operations. It is not. It is the single most consequential advantage the Moon holds over every other destination in the solar system. and it reshapes the entire strategy of human survival beyond Earth. To understand why, you need to understand what happens when that communication delay grows from seconds to minutes. Mars orbits the Sun at an average distance of roughly 140 million miles from Earth. But because both planets orbit independently, the actual distance between them changes constantly. At its closest approach, called opposition, Mars comes within about 34 million miles. At its farthest, when the Sun sits directly between the two planets, Mars recedes to roughly 250 million miles. The average distance that mission planners use for calculations falls around 140 million miles. A radio signal travelling at the speed of light takes between 3 minutes at closest approach and roughly 22 minutes at greatest separation to cross that gap. The round-trip delay, the time between sending a message and receiving a reply, ranges from 6 to 44 minutes. 44 minutes. Imagine a surgeon on Earth guiding an emergency medical procedure on Mars. The surgeon says, "Clamp the artery." 44 minutes later, the instruction arrives. The crew member applies the clamp, sends back a status update. 44 minutes after that, the surgeon learns whether the patient survived. By then, the patient has been bleeding for nearly an hour and a half since the original instruction was sent. Real-time guidance is impossible. Consultation is agonizingly slow. Every medical decision must be made locally, by crew members who are trained but not specialists, using equipment that cannot be resupplied for months. On the Moon, that same scenario unfolds in under 3 seconds. The surgeon speaks. 1.3 seconds later, the instruction arrives. The crew responds. 1.3 seconds after that, the surgeon sees the result. The communication loop is fast enough for genuine real-time collaboration. Earth-based experts can guide procedures, troubleshoot equipment failures, analyze data, and make recommendations as events unfold, rather than long after outcomes are already determined. This does not eliminate risk. People can still die on the Moon despite real-time communication with Earth. But it transforms the nature of emergencies from isolated crises managed by small crews with limited expertise into collaborative problems where the full weight of Earth's medical, engineering, and scientific resources can be brought to bear within seconds. The communication advantage extends far beyond medical emergencies. Engineering failures on a lunar base can be diagnosed in real time by ground teams with access to design documents, simulation tools, and decades of operational experience. When a carbon dioxide scrubber malfunctions, engineers on Earth can walk a crew member through repair procedures step by step, watching telemetry data as adjustments are made, catching mistakes before they cascade into larger failures. When a software glitch disables a critical system, programmers on Earth can write patches, upload them, and verify their function within minutes. On Mars, every troubleshooting cycle takes at minimum an hour of communication delay, and more typically several hours, once you account for the time needed to formulate responses, review options, and transmit instructions. This difference sounds incremental. It is not. It is the difference between operations that function like an extension of Earth-based infrastructure and operations that function as isolated outposts, making life or death decisions alone. The International Space Station operates with communication delays measured in fractions of a second, and even there, ground support is considered essential to crew safety. Controllers monitor systems around the clock. Engineers intervene when anomalies appear. Flight surgeons consult on medical issues in real time. The station's safety record depends fundamentally on this continuous connection to Earth. The Moon preserves that connection with only trivial delay. Mars severs it almost completely, but proximity offers more than communication speed. It offers something even more fundamental to sustained human presence: the ability to get there and back in a reasonable time frame. An Apollo mission took approximately 3 days to travel from Earth to lunar orbit. Modern spacecraft using similar trajectories achieve comparable transit times. 3 days is short enough that consumables, air, water, food can be packed for the journey without requiring enormous cargo capacity. 3 days is short enough that medical emergencies during transit while dangerous, are survivable with onboard supplies. 3 days is short enough that if something goes catastrophically wrong during a surface mission, a rescue flight from Earth could conceivably reach the Moon before supplies run out. Not easily, not cheaply, but conceivably. Compare this with Mars. A transit to Mars using current propulsion technology takes between 6 and 9 months depending on orbital alignment and trajectory choice. 6 months of life support. 6 months of radiation exposure during transit through deep space beyond Earth's magnetosphere. 6 months of muscle atrophy and bone loss in microgravity, unless the spacecraft provides artificial gravity, a technology that has never been implemented on a crewed vessel. 6 months, during which any medical emergency must be resolved entirely with onboard resources because no rescue mission can reach a Mars-bound crew faster than they can reach Mars themselves, and the transit time is only half the problem. Mars launch windows are dictated by orbital mechanics. Because Earth and Mars orbit the Sun at different rates, the planets align for efficient transit only once every 26 months. Miss a window, and you wait more than 2 years for the next one. This means that a crew on the Martian surface cannot simply decide to come home when supplies run low or equipment fails. They must wait for the correct orbital alignment, which may be months away. Total mission duration for a Mars surface stay, including transit both ways and the mandatory wait for the return window, stretches to roughly 2.5 to 3 years. The Moon imposes no such constraint. Launch windows to the Moon open multiple times per month. Transit takes 3 days. A crew member who develops a serious medical condition can theoretically be evacuated to Earth within a week. A critical spare part can be launched from Cape Canaveral or Kourou or Tanegashima and delivered to the lunar surface within days. The logistics pipeline between Earth and Moon is not instantaneous, but it operates on timescales measured in days rather than years. This difference is not merely convenient, it is transformative. Consider what this means for building infrastructure. Every habitat module, every power system, every life support unit, every scientific instrument destined for a lunar base can be delivered independently, tested on-site, connected to existing systems, and verified as functional before the next component arrives. If a module arrives damaged, it can be repaired using tools shipped on the next flight or replaced entirely. If a design flaw emerges during initial operations, engineers on Earth can redesign the component, manufacture a replacement, and ship it within weeks or months. On Mars, infrastructure must be pre-positioned in massive automated shipments years before crews arrive. Everything must work on the first try because replacement parts take 2.5 years to deliver. A single critical failure in a pre-positioned habitat could render an entire mission uninhabitable before humans even launch. The engineering margins required for Mars infrastructure are consequently enormous, driving costs and complexity to levels that remain beyond current budgets and technology. The Moon allows iterative development. Build a small shelter, test it for a month, identify problems, ship improvements, expand, test again. This cycle of build, test, learn and improve is the same process that transformed aviation from the Wright Flyer to modern airliners. The same process that turned early computing from room-sized machines into pocket devices. The same process that built the International Space Station module by module over 2 decades. Iteration requires proximity. It requires the ability to fail, learn, and try again without catastrophic delay. The Moon provides that proximity. Mars does not. NASA's March 2026 announcement of the Artemis Base Camp plan illustrates exactly this iterative philosophy. The $20 billion initiative was structured into 3 phases spread across a decade, precisely because the Moon's closeness allows phased construction. Phase 1 focuses on frequent crewed and robotic missions delivering rovers, habitats, and technology payloads. Phase 2 introduces semi-habitable infrastructure and regular logistics flights, including a pressurized rover developed with JAXA that would allow astronauts to drive across the lunar surface in a shirt-sleeve environment for days at a time. Phase 3 targets permanent infrastructure with nuclear and solar power systems, crewed and uncrewed rovers, a lunar GPS network, and habitation modules designed for extended occupation. Each phase depends on the previous one succeeding. Each phase allows correction if the previous one revealed unexpected problems. This is only possible because the Moon is 3 days away. If the first habitat module develops a micrometeorite puncture after 6 months, a repair mission can reach the site within a week. If the nuclear fission reactor prototype underperforms, a redesigned unit can be delivered on the next cargo flight. If the pressurized rover encounters terrain it cannot navigate, route planning can be adjusted using fresh orbital imaging transmitted to Earth in real time. The decision to pause the Lunar Gateway, the orbital space station originally planned as a staging point between Earth and the lunar surface, further underscores the proximity advantage. In March 2026, NASA announced a strategic pivot away from Gateway toward a surface-first approach. The rationale was both technical and strategic. Building an orbital station added complexity and cost to every surface mission. Astronauts would need to transfer between vehicles in lunar orbit, adding risk and time to operations that were already extraordinarily complex. The surface-first approach recognizes that the Moon is close enough to reach directly from Earth without an orbital way station, simplifying the architecture and redirecting resources toward the actual goal, putting humans on the surface and keeping them there. This pivot also reflected geopolitical realities. China's lunar program has been advancing steadily, with the Chang'e 7 mission scheduled for 2026, targeting the lunar South Pole for water ice prospecting. The International Lunar Research Station, a Chinese-led initiative with international partners, aims to establish permanent infrastructure at the South Pole within the next decade. The urgency of establishing a sustained American and Allied presence at the South Pole accelerated the shift toward direct surface operations, but that urgency could only translate into action because the Moon's proximity makes rapid, frequent missions feasible with existing and near-term rocket technology. Proximity also transforms the psychology of sustained presence. Astronauts on the Moon can see Earth, not as a pale blue dot reduced to a single pixel as it appears from Saturnian distances, but as a vivid, luminous sphere hanging in the black sky, visibly rotating, cloud patterns shifting, continents recognizable. Earth from the lunar surface is roughly 4 times the apparent diameter of the Moon, as seen from Earth. It dominates the sky during lunar night on the near side, casting faint Earthshine across the surface. This visual connection matters more than engineers typically acknowledge. Every study of human psychology in extreme isolation emphasizes the importance of connection to home. Antarctic winter rover crews, submarine personnel, and space station astronauts all report that psychological well-being correlates strongly with communication frequency and perceived connection to family and familiar environments. Astronauts on the Moon can video call their families with less delay than a typical international phone call experience 20 years ago. They can watch news broadcasts, follow sports, stream music, and participate in conversations with minimal disruption. The psychological tether to Earth remains intact. On Mars, that tether stretches to the breaking point. A video message takes up to 22 minutes to arrive. Real-time conversation is impossible. Crew members exist in a communication bubble where every exchange with Earth is delayed, asynchronous, and emotionally attenuated by the knowledge that the person speaking to you finished their sentence nearly half an hour ago. Studies of analog Mars missions, where crews simulate Martian isolation in remote locations on Earth, consistently report increased psychological stress, interpersonal conflict, and feelings of abandonment compared to conditions simulating closer destinations. A crew on Mars is psychologically alone in a way that a crew on the Moon never has to be. The rescue equation deserves particular attention because it represents perhaps the starkest contrast between lunar and Martian operations. On the Moon, rescue is difficult but physically possible. If a crew faces a catastrophic failure that they cannot repair, Earth can launch an emergency mission. The spacecraft would reach lunar orbit in 3 days, descent to the surface, rendezvous with the stranded crew, and emergency evacuation could theoretically be accomplished within a week of the initial distress call. This timeline is aggressive. It assumes a rocket and spacecraft are available on short notice, which requires maintaining standby launch capability. It assumes the stranded crew can survive on emergency supplies for that duration. It assumes the rescue vehicle can land near enough to the distressed habitat for transfer. None of these assumptions are trivial, but none of them are physically impossible either. On Mars, rescue is essentially a fiction. A crew on Mars that faces a life-threatening emergency cannot be reached by any spacecraft launched from Earth in less than 6 months. During a significant portion of the Martian orbital cycle, no trajectory from Earth to Mars exists at all, because the orbital geometry does not permit efficient transfer. A crew that suffers a catastrophic failure during the wrong portion of the Mars-Earth cycle faces a wait of over a year before any rescue vehicle could even depart Earth, followed by additional months of transit. Practically speaking, a crew on Mars either solves its own problems or dies. There is no cavalry. This is not an exaggeration for dramatic effect. It is the blunt mathematical reality of orbital mechanics. Mars advocates acknowledge this constraint and argue that crews can be trained and equipped to handle emergencies independently. They point to submarine crews and Antarctic expeditions that operate for months without external rescue capability. These analogies have merit, but they also have limits. Submarine crews operate in an environment where the physics of survival are well understood after decades of operational experience. Antarctic expeditions occur on a planet where emergency evacuation, while difficult, remains physically achievable by aircraft. Neither analogy captures the true isolation of a Mars crew, separated from all of Earth's resources by millions of miles of vacuum with no possibility of timely assistance. The Moon does not eliminate the danger of human spaceflight. It does not make living in space safe. What it does is create an environment where the risks can be managed through the same mechanisms that have enabled every previous expansion of human presence into hostile environments. Incremental extension, frequent resupply, rapid communication, emergency evacuation capability. These mechanisms require proximity, and the Moon provides it. There is another dimension to proximity that rarely appears in public discussions of lunar strategy, but profoundly shapes engineering decisions: the mass budget. Every kilogram of payload delivered to the lunar surface costs thousands of dollars in launch costs. Reducing that cost requires either cheaper rockets or lighter payloads. But the Moon's relative closeness means that existing rockets, Falcon Heavy, SLS, and the emerging class of super heavy vehicles like Starship can deliver meaningful cargo to the lunar surface without requiring propulsion technologies that do not yet exist. The mission architecture for the Moon is fundamentally simpler than for Mars. A lunar cargo flight launches, performs a translunar injection burn, coasts for 3 days, and executes a powered landing. No interplanetary cruise phase lasting months. No complex aerobraking entry through a thin atmosphere at hypersonic speeds. No orbital insertion burn after a half-year transit. The shorter mission timeline means less consumable mass devoted to keeping systems alive during transit, freeing more of the rocket's capacity for actual payload. A heavy-lift rocket that can deliver 20 tons of useful cargo to the lunar surface may deliver only 5 tons to Mars after accounting for the additional propellant, consumables, and thermal protection required for the longer, more complex journey. This mass advantage compounds across every shipment. More payload per launch means fewer launches required to build equivalent infrastructure. Fewer launches mean lower costs, faster construction timelines, and reduced operational risk. The logistics pipeline to the Moon is not merely faster than the pipeline to Mars, it carries more cargo per flight, requires less propellant, and operates with wider launch windows. These advantages are not marginal, they are multiplicative. When Artemis program architects designed the phased base camp concept, they explicitly relied on this logistics advantage. The plan assumes regular cargo deliveries using commercial lunar payload services, the same CLPS program that has already demonstrated commercial landings on the lunar surface with missions like Intuitive Machines' IM-1 and IM-2 flights. These commercial deliveries do not require the enormous SLS rocket for every shipment. Smaller, cheaper commercial vehicles can carry scientific instruments, spare parts, consumables, and construction materials on frequent flights. The Moon's proximity makes commercial lunar logistics economically viable in a way that commercial Mars logistics is not. Artemis 2, currently flying as these words reach you, represents the human-rated validation of this logistics chain. 4 astronauts, Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen, are at this moment looping around the Moon aboard Orion, testing the spacecraft systems that will eventually carry crews to the surface. The mission launched on April 1st, 2026, after years of delays related to heat shield concerns, life support issues, and the inevitable complications of building hardware designed to keep humans alive in deep space. The delays themselves illustrate how difficult even visiting the Moon remains. But the mission is flying, and its purpose is explicitly to validate the transportation link between Earth and the Moon, confirming that the proximity advantage can be converted into operational reality. The first crewed landing is now targeted for Artemis 4 in early 2028. Artemis 3, repurposed in late February 2026, will conduct rendezvous and docking tests in low Earth orbit with one or both commercial lunar landers, SpaceX's Starship HLS and Blue Origin's Blue Moon, along with testing the new Axiom spacesuit. This restructuring reflects another proximity-enabled strategy: test complex systems close to home before committing them to distant operations. The Moon is far enough to require serious engineering, but close enough to allow iterative testing without betting everything on a single mission. Each Artemis flight builds on the previous one, extending capability incrementally. After Artemis 5, NASA anticipates approximately 1 lunar mission per year. Each mission will extend surface, stay duration, expand infrastructure, and increase the complexity of operations. Early missions will last days, later missions will last weeks. Eventually, missions will overlap, with one crew arriving before the previous crew departs, creating the first continuous human presence on another world. This ladder of increasing duration and complexity is only possible because each rung can be reached from the previous one within days rather than years. None of this makes the Moon easy. Nothing about proximity eliminates the vacuum, the radiation, the dust, the thermal extremes, or the gravitational deficit described in every brutal detail earlier. Astronauts on the lunar surface will still wear spacesuits that must function flawlessly in an environment designed to destroy them. They will still breathe recycled air inside habitats that must withstand thermal cycling, micrometeorite impacts, and dust infiltration. They will still face radiation exposure that demands shielding solutions not yet fully validated. Proximity does not make the Moon gentle. What proximity does is make the Moon learnable. It creates the conditions under which humans can fail on the Moon and survive, learn from the failure, adjust, and try again. It creates a feedback loop between Earth and the lunar surface that operates on timescales compatible with human problem-solving. It makes the difference between a one-shot expedition and a sustained program of incremental expansion. It is the difference between exploration and habitation. Every great expansion of human civilization into hostile environments followed this pattern. Humans did not colonize the Arctic in a single expedition. They made short forays, returned home, improved their equipment, went back, stayed longer, built better shelters, established supply chains, and gradually extended their presence until permanent settlements became viable. The same pattern unfolded in deep-sea exploration, in high-altitude mountaineering, in Antarctic research stations. Each iteration required the ability to return to safety, analyze results, make improvements, and try again. Each iteration required proximity to existing infrastructure, The Moon sits at exactly the right distance to enable this process, close enough to support frequent missions, close enough for real-time communication, close enough for emergency evacuation, close enough for regular resupply, far enough to present genuine deep space challenges that prepare humanity for eventually going farther. It is not a safe destination. It is a survivable one, and that distinction, the distinction between safe and survivable, between comfortable and learnable, may determine whether humanity becomes a spacefaring species or remains permanently confined to one fragile planet. But proximity alone is not sufficient. A close destination that offers nothing, no resources, no shelter options, no strategic advantages, would still be a dead end regardless of how quickly you can reach it. The Moon must offer more than just nearness. It must offer reasons to stay, features that can be exploited, materials that can be converted into survival infrastructure. The next chapter examines whether the Moon provides these resources, and the honest answer is more complicated and more interesting than most people realize. Proximity gets you to the Moon. It does not keep you there. Staying requires something the Moon was never supposed to offer: resources. For decades after Apollo, the conventional wisdom held that the Moon was essentially a dead rock, geologically inert, chemically barren, and utterly devoid of the materials needed to sustain life. The samples Apollo astronauts brought home confirmed a world of basaltic rock, powdered regolith, and mineral compositions that contain no water, no organic compounds, and no easily extractable volatiles. The Moon appeared to be exactly what it looked like from Earth: a desiccated, airless wasteland, with nothing to offer except scientific curiosity and bragging rights. That picture began changing in the 1990s, and it has been growing steadily more complex ever since. The story of lunar resources is not a story of abundance. It is not a tale of hidden riches waiting to be claimed. It is something subtler, more uncertain, and ultimately more interesting: a story of trace materials in unexpected places, environmental features that could be exploited through clever engineering, and strategic locations where geography itself becomes a survival advantage. Understanding this story requires examining the south pole of the Moon, because nearly every serious plan for sustained lunar presence converges on that single region, and the reasons reveal how resource strategy on another world actually works. The lunar south pole is special because of geometry. The Moon's rotational axis tilts only 1.5 degrees relative to the plane of its orbit around the Sun. Compare this with Earth's tilt of 23.5 degrees, which gives us seasons, and you begin to see the consequences. On Earth, the large axial tilt means that the poles experience months of continuous daylight in summer and months of continuous darkness in winter, with the Sun climbing high above the horizon during its lit phase. On the Moon, the tiny tilt means the Sun never rises far above the horizon at the poles. It skims along the ridgelines, illuminating peaks and crater rims while leaving the floors of deep craters in permanent shadow. This creates two features found nowhere else on the Moon, and possibly nowhere else in the inner solar system in such accessible combination. The first feature is peaks of near-eternal light. Several ridgelines and crater rims near the South Pole receive sunlight for the vast majority of the year. Data from the Lunar Reconnaissance Orbiter shows that the best locations along the Shackleton-de Gerlache Ridge remain illuminated for up to roughly 90 to 94% of the time, with no single point receiving truly perpetual sunlight. The longest continuous period of darkness at the most favourable sites lasts roughly 40 to 50 hours, short enough to bridge with battery storage rather than requiring massive long-duration power solutions. For a solar-powered habitat, this is transformative. Everywhere else on the Moon, the 14-day night imposes a brutal constraint on energy generation. A base at the equator would need either enormous battery banks capable of storing 2 weeks of power consumption, or an alternative energy source entirely independent of sunlight. Either option adds mass, cost, and complexity that strain the logistics budget. At the South Pole peaks, solar panels can generate power almost continuously, with only brief interruptions that batteries can handle comfortably. The energy problem does not disappear, but it shrinks from an existential crisis to an engineering challenge. The second feature is those permanently shadowed regions. The floors of deep craters near the poles have not seen direct sunlight for billions of years. Temperatures in these shadows plunge below -230 degrees Celsius, approaching the temperatures found on the surfaces of distant objects in the outer solar system. These ultra-cold zones act as natural cold traps, and for decades, scientists hypothesized that volatile compounds, particularly water ice, might have accumulated there over geological time, delivered by cometary impacts, asteroid collisions, and solar wind interactions with the oxygen-rich minerals in the regolith. The hypothesis was not wishful thinking. The physics supported it. Water molecules, whether released from impacting comets or generated by solar wind protons reacting with metal oxides in the regolith, would migrate across the lunar surface in ballistic hops, bouncing from point to point until they either escaped into space, were destroyed by ultraviolet radiation, or landed in a cold trap where temperatures were low enough to prevent further migration. Once trapped, the ice could persist for billions of years in the permanent darkness, accumulating molecule by molecule into deposits mixed with regolith. The first indirect evidence arrived in 1994 when the Clementine spacecraft detected radar signatures from the South Pole consistent with ice deposits. 4 years later, the Lunar Prospector Orbiter detected elevated hydrogen concentrations at both poles, strengthening the case. In 2009, NASA's L-Cross mission deliberately crashed a Centaur rocket stage into Cabeus crater near the South Pole, then flew a trailing spacecraft through the resulting debris plume. The instruments detected water vapor and ice crystals in the ejecta, providing the first direct confirmation that water exists in at least some permanently shadowed craters. In 2018, a team led by Shuai Li at the University of Hawaii published the first direct spectroscopic detection of surface water ice at the lunar poles using data from NASA's Moon Mineralogy Mapper instrument aboard India's Chandrayaan-1 orbiter. The detections were sparse. Ice signatures appeared in roughly 3.5% of cold trap surfaces examined, but they were definitive. Water ice exists on the lunar surface. The question has always been how much, and this is where honesty becomes essential, because the most recent data complicates the narrative significantly. In March 2026, a study published in Science Advances by Lee and colleagues delivered results that challenged assumptions about lunar ice abundance. Using NASA's ShadowCam, an ultra-sensitive camera aboard South Korea's Korea Pathfinder lunar orbiter, the team examined permanently shadowed regions with higher resolution and sensitivity than any previous instrument. ShadowCam was specifically designed to image the darkest lunar craters by capturing reflected light that bounces off illuminated crater walls into the shadows below. The researchers looked for two diagnostic optical signatures of water ice: elevated reflectance compared to surrounding regolith, and a distinctive forward scattering pattern where ice-bearing surfaces redirect light differently than rock. The results were sobering. Across the permanently shadowed regions examined, the team found no evidence of water ice at abundances above approximately 20 to 30 weight%. If thick, relatively pure ice deposits existed on the surface of these craters, ShadowCam should have detected them. It did not. A few small locations showed both elevated reflectance and forward scattering behavior, consistent with ice concentrations above 10%, but these were isolated patches, not the widespread deposits that the most optimistic models had predicted. This finding does not mean the moon is dry. It means the surface of the permanently shadowed regions probably does not contain abundant, easily accessible ice sitting in thick, pure layers waiting to be scooped up. Lower concentration ice, mixed into the regolith at levels below ShadowCam's detection threshold of roughly 20 to 30%, remains entirely possible. Some measurements were consistent with mixtures containing less than 10% water ice by weight. The team noted that future missions with detection limits Below 1% will be needed to resolve whether widespread low-concentration ice exists. Crucially, ShadowCam can only examine the optical surface, the top few millimeters of regolith. It tells us nothing about what lies beneath. Subsurface ice deposits, buried under centimeters or meters of regolith that accumulated after the ice was deposited, would be invisible to any camera-based instrument. The LCROSS impact detected water in ejecta blasted from below the surface, suggesting that at least some subsurface ice exists. Neutron spectrometer data from Lunar Prospector detected elevated hydrogen consistent with water-bearing material within the top meter of soil at both poles. The evidence for subsurface ice remains strong even as the case for abundant surface ice has weakened. This matters enormously for mission planning. Extracting surface ice is relatively simple. Drive a rover into a shadowed crater, scoop up ice-bearing regolith, heat it, and collect the water vapor. Extracting subsurface ice requires drilling, excavation, or thermal extraction techniques that are more complex, more energy-intensive, and less well-tested. But neither approach is impossible, and both are the subject of active technology development. NASA's upcoming support for the LUPEX mission, a JAXA-ISRO collaboration planned for no earlier than 2028, includes a neutron spectrometer specifically designed to map subsurface hydrogen distributions at fine spatial scales. China's Chang'e 7 mission, scheduled for 2026, will deploy a Hopper spacecraft equipped with a water molecule analyzer designed to jump into permanently shadowed craters and search for direct evidence of ice. Multiple nations are converging on the South Pole with instruments designed to answer the question that ShadowCam could not: how much water is actually there, and in what form? The honest assessment as of today is that water ice almost certainly exists at the lunar South Pole, but its abundance, distribution, and accessibility remain uncertain. The most optimistic scenarios, in which thick ice deposits can be mined with simple equipment, have become less likely in light of ShadowCam data. The most pessimistic scenario, in which no usable ice exists at all, is contradicted by L-cross results and neutron spectrometer data. The reality probably falls somewhere in between patchy, low-concentration ice mixed with regolith, possibly with more concentrated deposits buried beneath the surface, requiring significant engineering to extract but not fundamentally out of reach. Even in the conservative case, water extraction on the moon would be revolutionary. Water is not just something to drink. It is oxygen to breathe. It is hydrogen and oxygen to burn as rocket propellant. Every kilogram of water produced on the lunar surface is a kilogram that does not need to be launched from Earth, saving roughly 10 to 20 kilograms of propellant that would have been needed to lift that water through Earth's gravity well. If lunar water can be extracted at scale, even modest scale, it fundamentally changes the economics of cislunar operations. Spacecraft refueled with lunar-derived propellant could travel to Mars, to asteroids, to destinations across the inner solar system without carrying all of their fuel from Earth. The moon becomes not just a destination but a gas station, a logistics node in a larger transportation network. But water is not the only resource the moon offers. The regolith itself, despite being a hazardous nuisance in terms of dust contamination, is a construction material of extraordinary potential. Lunar regolith is rich in oxides, silicon dioxide, aluminum oxide, iron oxide, calcium oxide, magnesium oxide, and titanium dioxide, among others. These minerals can theoretically be processed to extract oxygen, metals, and construction materials using techniques collectively called in situ resource utilization, or ISRU. Oxygen extraction from regolith has been demonstrated in laboratory conditions using several methods. Hydrogen reduction heats regolith in the presence of hydrogen gas, pulling oxygen out of iron oxide minerals and producing water as a byproduct. Molten salt electrolysis dissolves regolith in a molten salt bath and uses electric current to separate oxygen from the melt. Carbothermal reduction uses carbon monoxide at high temperatures to strip oxygen from silicate minerals. Each method has trade-offs in energy requirements, equipment complexity, and yield, but all have been demonstrated at bench scale with real or simulated lunar material. The challenge is scaling these processes to produce operationally meaningful quantities of oxygen using equipment that can be delivered to the Moon and operated reliably in the lunar environment. Beyond oxygen, the regolith contains metals that could be used for construction. Iron extracted from ilmenite, a titanium iron oxide mineral common in lunar basalts, could potentially be refined into structural steel using solar furnaces or electric arc processes. Aluminum is abundant in the lunar highlands but requires more energy-intensive extraction methods. Titanium, while present, exists in concentrations that make extraction challenging without sophisticated refining infrastructure. None of these processes are ready for deployment today, but they represent a long-term pathway toward reducing dependence on Earth for structural materials. The regolith also offers immediate value as radiation shielding. Piling lunar soil over a habitat structure provides mass shielding against cosmic rays and solar particle events. A layer of regolith roughly 2 to 3 meters thick reduces radiation exposure to levels comparable to the natural background radiation on Earth's surface. This approach requires no exotic technology, just the ability to move and pile dirt, a capability that robotic bulldozers and excavators can provide. Several Artemis Base Camp concepts include regolith shielding as a primary radiation mitigation strategy, using the Moon's own material to solve one of its most dangerous problems. But regolith is not just a material to pile on top of structures, it is a potential feedstock for construction itself. Researchers have demonstrated that lunar regolith can be sintered heated to just below its melting point to fuse loose particles into solid blocks without requiring any binding agent shipped from Earth. The process exploits the glassy component of lunar soil, created by billions of years of micrometeorite impacts that partially melted surface material into tiny spheres of volcanic glass. When heated to roughly 1100 degrees Celsius using concentrated solar energy or electric furnaces, these glassy particles soften and bond together, forming a dense ceramic material with compressive strength comparable to concrete. The implications are significant. If sintering can be performed reliably on the lunar surface using solar concentrators, or the waste heat from nuclear reactors, it enables the production of building blocks from local material using local energy. Bricks, tiles, paving stones, and structural panels could be manufactured at the base site without importing construction materials from Earth. Robotic systems could collect regolith, feed it into a sintering furnace, and produce standardized building elements that are assembled into radiation shields, blast berms, landing pads, roadbeds, and structural walls. Each kilogram of sintered block produced on the Moon represents a kilogram that did not need to ride a rocket through Earth's atmosphere and across 240,000 miles of vacuum. Several research groups have pushed this concept further. Three-dimensional printing using regolith as feedstock has been demonstrated in laboratory conditions using both simulated and actual lunar soil samples returned by China's Chang'e 5 mission. The European Space Agency has partnered with architecture firms to develop a concept called the lunar habitat, in which a dome-shaped structure is printed layer by layer using a regolith binding process, with the printed shell serving as both structural support and radiation shielding. The design calls for a thin pressurized membrane deployed from Earth and then buried under a printed regolith shell several meters thick. The membrane provides atmospheric containment while the printed shell provides structural integrity and radiation protection. No concept like this has been tested on the lunar surface, but the component technologies, robotic regolith handling, solar sintering, and additive manufacturing with granular feedstock have each been demonstrated at varying levels of maturity in terrestrial laboratories and reduced gravity environments. The challenge, as with every ISRU application, is the gap between laboratory demonstration and operational deployment. A sintering furnace that works beautifully in a climate-controlled laboratory in Cologne faces vastly different conditions on the lunar surface. Thermal cycling between day and night stresses equipment. Dust infiltrates mechanical systems, Reduced gravity alters the flow behavior of granular material. Power availability depends on the time of lunar day and the status of solar and nuclear systems. Each of these factors must be addressed through testing that can only occur on the Moon itself, which circles back to the proximity advantage. Each test informs the next design iteration, and each iteration can be shipped and installed within months rather than years. The concept of lava tube habitation takes this shielding approach to its logical extreme. Orbital imaging and gravity mapping have identified features consistent with intact lava tubes beneath the lunar surface, particularly in the Mare basalt regions. These tubes, formed billions of years ago when lava flowed beneath solidified surface crusts, could be enormous. Some estimates suggest tube diameters of hundreds of meters, large enough to contain entire pressurized habitats within their naturally shielded interiors. A lava tube with tens of meters of solid basalt overhead would provide near-complete shielding against radiation and micrometeorites while maintaining stable temperatures year-round, insulated from the extreme thermal cycling of the surface. Confirming the existence, structural integrity, and accessibility of specific lava tubes remains an engineering challenge. No mission has yet entered a lunar lava tube or directly imaged one from the interior. Several candidate skylights collapse holes in the ceilings of lava tubes have been identified in orbital imagery, and robotic missions designed to descend into these openings are in various stages of planning. If intact, accessible lava tubes exist near the South Pole or in other strategically useful locations. They could provide ready-made shelters that dramatically reduce the construction burden for a sustained base. Power is perhaps the most solvable of the major infrastructure challenges, though it remains formidable. Solar power at the peaks of near-eternal light provides the primary energy source for early base operations, but solar panels alone cannot sustain a growing base through even brief periods of darkness or supply the energy-intensive processes required for ISRU. The Artemis Base Camp plan addresses this through a nuclear fission surface power system called Lunar Reactor 1, targeted for deployment by 2030. NASA awarded contracts for the development of a 40-kilowatt fission surface power system in 2022. The system uses a compact nuclear reactor to generate electricity through a Stirling engine conversion system, operating independently of sunlight. 40 kilowatts is modest by terrestrial standards, roughly enough to power 8 to 10 average American homes, but on the Moon, it represents a transformative capability. It enables continuous operations during lunar night. It powers ISRU processing equipment. It provides heating for habitats during the 14-day darkness periods that would otherwise require massive battery storage. Multiple reactor units could be deployed to scale power capacity as the base grows. Nuclear power on the Moon is not without complications. Reactor mass must be delivered from Earth, adding to launch costs. Radiation from the reactor itself must be shielded, typically by placing the unit behind a regolith berm at a safe distance from habitats. Maintenance of nuclear systems in the lunar environment requires capabilities that have not yet been demonstrated. But the fundamental technology is well understood, and several nations have operated compact nuclear reactors in remote terrestrial environments for decades. Adapting this technology for the Moon is an engineering challenge, not a physics challenge. Mobility on the lunar surface represents another critical infrastructure element. Apollo astronauts explored on foot, and during the last 3 missions, using the Lunar Roving Vehicle, an open-frame electric car with a range of roughly 35 kilometers. For sustained operations, crews need vehicles that provide much greater range and protection. The Artemis plan includes a lunar terrain vehicle for unpressurized short-range transport and a pressurized rover developed in collaboration with JAXA that would allow astronauts to live and work inside a shirt-sleeve environment for up to 30 days while traversing hundreds of kilometers from the base. A pressurized rover fundamentally changes the operational concept. Instead of limiting exploration to the walking or driving range achievable during a single EVA, crews can undertake multi-day traverses across the lunar surface, sleeping, eating, and conducting science inside the rover while parking at sites of geological or resource interest. This turns the base from a fixed point of operations into the anchor of an exploration network spanning significant portions of the South Pole region. Crews can survey multiple permanently shadowed regions, prospect for ice at various locations, and characterize terrain for future infrastructure placement, all while maintaining a habitable environment. Dust mitigation deserves particular attention because it represents one of the most persistent unsolved challenges of sustained lunar operations. Every system that interacts with the exterior environment, airlocks, spacesuits, rovers, tools, sample containers, becomes a vector for dust infiltration into habitable spaces. Apollo crews tried brushing dust off their suits before re-entering the lunar module. It did not work. The electrostatically charged particles clung to fabric, metal, and polycarbonate with tenacity that defied mechanical removal. Modern airlock concepts for lunar habitats address this problem through multi-stage designs that attempt to contain dust before it reaches the pressurized interior. One approach uses a suit lock, in which the spacesuit is mounted on the exterior wall of the habitat. The astronaut climbs into the suit from inside the habitat through a rear entry hatch, seals the hatch, and detaches the suit from the wall to begin EVA. Upon return, the suit docks back to the wall and the astronaut climbs out into the habitat without ever bringing the suit's dust-coated exterior into the pressurized volume. The suit remains outside at all times. Only the astronaut's body passes between interior and exterior environments. This concept eliminates the largest source of dust contamination, dragging an entire spacesuit through a conventional airlock, but it does not solve the problem entirely. Tools, samples, and equipment must still pass through airlocks. Gloves that contact regolith during EVA still accumulate fine particles that can transfer to interior surfaces. Suit lock seals themselves must resist dust accumulation at the mating surface, a challenge that requires materials and engineering solutions still under active development. Electrodynamic dust shields, which use oscillating electric fields to repel charged particles from surfaces, have been demonstrated in laboratory conditions and represent a promising supplementary technology, but their long-term durability in the lunar environment remains unproven. The life support architecture of a sustained lunar base presents an equally demanding engineering challenge that moves well beyond the portable systems used on Apollo and even beyond the more sophisticated systems aboard the International Space Station. A lunar habitat designed for multi-month occupation must achieve water recycling efficiencies approaching 98%. On the ISS, the water recovery system processes urine, humidity, condensate, and wastewater to recover roughly 90 to 93% of available water. The remaining 7 to 10% is lost and must be resupplied from Earth. For a lunar base operating farther from routine resupply, that loss rate must be driven even lower. Every percentage point of improved recovery reduces the mass of water that must be shipped from Earth and extends the operational autonomy of the base between resupply flights. Carbon dioxide scrubbing requires similar advances. The ISS uses a system called the Carbon Dioxide Removal Assembly, which captures carbon dioxide from cabin air using zeolite beds and vents it overboard. This approach works in low Earth orbit where atmospheric gases are expendable, but on the Moon, venting carbon dioxide means losing the carbon and oxygen atoms it contains. A more advanced system would capture the carbon dioxide and feed it into a Sabatier reactor or similar process that combines carbon dioxide with hydrogen to produce methane and water. The water can be electrolyzed back into oxygen for breathing and hydrogen for recycling into the reactor. This closed-loop approach minimizes atmospheric losses and reduces resupply requirements, but it adds complexity, mass, and power demands to the life support system. Food production represents perhaps the longest-term challenge, and the one that most clearly separates visiting from living. Apollo crews ate pre-packaged meals for their short surface stays. ISS crews eat a combination of pre-packaged and rehydrated foods shipped from Earth on cargo flights every few months. Neither approach scales to a permanent lunar base, with long surface stays and limited cargo capacity. Even modest supplemental food production on the Moon, growing fresh greens, herbs, or vegetables in pressurized greenhouse modules would reduce the mass of food shipments, provide nutritional variety, improve crew morale, and begin developing the agricultural knowledge needed for more ambitious future settlements. Plant growth experiments have been conducted aboard the International Space Station for years. The veggie and advanced plant habitat systems have successfully grown lettuce, radishes, chili peppers, and other crops in microgravity. These experiments demonstrated that plants can germinate, grow, and produce edible biomass in the space environment, although yields remain far below what would be needed to feed a crew. Lunar gravity at 1/6 Earth normal may actually benefit plant growth compared to microgravity, since gravity drives water drainage through root zones and assists nutrient transport in ways that microgravity disrupts. However, lunar greenhouse modules face unique challenges: radiation shielding for plants as well as crew, power requirements for supplemental lighting during the 14-day night, thermal regulation to prevent freezing or overheating, and the logistical burden of shipping growth media, seeds, nutrients, and water to get the system started. No one expects a lunar base to achieve food self-sufficiency in the foreseeable future. The goal is incremental supplementation, growing enough fresh produce to meaningfully improve crew diet and health, while accumulating operational experience with closed-environment agriculture. Each harvest teaches lessons about plant biology under lunar conditions, water and nutrient cycling, pest and pathogen management in sealed environments, and the integration of biological systems with engineered life support. These lessons feed directly into the design of more ambitious agricultural systems for future bases and for eventual Mars habitation. Picture a day at a South Pole base a decade from now. A crew of 4 wakes inside a pressurized habitat module roughly the size of a large motorhome, buried under 2 meters of piled regolith. The interior is lit by adjustable LEDs that simulate terrestrial daylight spectra. Morning coffee is brewed using water that has been recycled through the life support system dozens of times since it was originally shipped from Earth, or, if ISRU extraction is operational, water that was once ice trapped in a permanently shadowed crater a few kilometers away. The crew reviews the day's schedule via communication link, with mission control in Houston, the round-trip delay so negligible that conversations feel essentially normal. 2 crew members suit up for EVA using the suit lock system, climbing into their Axiom-derived surface suits through rear entry hatches without ever bringing the dust-encrusted exteriors into the cabin. They drive the unpressurized lunar terrain vehicle to a nearby permanently shadowed region where a robotic drill has been extracting regolith samples for volatile analysis. They swap out full sample containers for empty ones, inspect the drill's mechanical components using a checklist developed from the previous mission's maintenance experience, and photograph surface features for geological mapping. Every image, every data point, every verbal observation is transmitted to Earth in near real time, where hundreds of scientists and engineers monitor, analyze, and archive the information. The other 2 crew members work inside the habitat. One monitors the oxygen extraction demonstrator, a small reactor that heats batches of regolith under hydrogen flow and collects the water vapor produced when iron oxides give up their oxygen. The reactor produces only a few liters of water per day, at this stage a fraction of what the crew consumes, but the data it generates informs the design of a full-scale unit scheduled for delivery on the next cargo flight. The second crew member tends the greenhouse module, harvesting a small crop of lettuce and recording growth metrics. The lettuce is not a significant caloric contribution. It is a proof of concept and a morale booster. Fresh green food on a world of grey dust. In the afternoon, the EVA team returns. The suit lock system captures the worst of the dust contamination, but trace particles still find their way through seals and settle on interior surfaces overnight. A weekly cleaning protocol addresses the accumulation, using electrostatic wipes and HEPA filtration to keep airborne particle concentrations below safety thresholds. The protocol was developed based on lessons learned from the previous crew's experience and will be refined based on this crew's observations. Nothing about this day is glamorous. Nothing about it suggests a thriving city or a comfortable settlement. It sounds more like the daily routine aboard a submarine on a long deployment than life in a science fiction colony. And that is precisely the point. Sustained human presence on the moon will not look like science fiction. It will look like hard, careful, methodical work conducted by small crews in cramped quarters, supported by a logistics pipeline from Earth, producing incremental advances in capability that compound over years into something that future historians may eventually recognize as the beginning of humanity's permanent expansion beyond its home world. The combination of these elements, location strategy at the South Pole, potential water ice resources even if sparse, regolith as shielding and construction feedstock, solar power supplemented by nuclear fission, and pressurized mobility does not create a comfortable living environment. It creates something far more important, a plausible architecture for reducing dependence on Earth, shipment by shipment, capability by capability, year by year. No single resource or feature is sufficient on its own. Water ice alone does not sustain a base. Solar power alone does not protect against radiation. Regolith shielding alone does not provide air or water, but assembled together, these elements begin to form an ecosystem of mutual support, where each resource addresses a specific survival challenge and each capability enables the next. This is what distinguishes the lunar resource story from naive optimism. Nobody credible is claiming the moon has everything humans need. The argument is more measured and more honest than that. The moon has enough to begin reducing the logistical burden on Earth, not eliminating it, not achieving independence, reducing it. And the pace of that reduction can be calibrated by proximity. Each mission tests a new extraction technique or deploys a new infrastructure element, and the results inform the next mission months later rather than years later. Consider the progression. The first Artemis surface missions will rely entirely on supplies brought from Earth. Astronauts will drink Earth water, breathe Earth oxygen, eat Earth food, and burn Earth fuel. Everything consumed during the mission arrives on the same vehicle or on preceding cargo flights. This is Apollo-style logistics applied to slightly longer surface stays. Nothing is produced on site, but embedded in those early missions are ISRU demonstration experiments. Small-scale oxygen extraction units will process samples of regolith and measure yields. Water prospecting instruments will map ice distributions in permanently shadowed regions. Solar power systems will log performance data across multiple lighting conditions. Each experiment generates data that feeds into the design of the next generation of equipment. If oxygen extraction proves viable at the demonstrated scale, a larger unit flies on the following mission. If water ice is found in accessible concentrations, extraction hardware is prioritized for near-term deployment. Within a decade of sustained operations, the goal is to produce at least some consumables locally. Oxygen, extracted from regolith supplements, or replaces Earth-supplied air stocks. Water, extracted from ice, if available, reduces the mass of life support consumables that must be shipped from Earth. Propellant produced locally refuels surface vehicles and possibly ascent stages, dramatically reducing the cost of return flights. Each local production capability that comes online subtracts mass from the Earth-to-Moon logistics chain and redirects that launch capacity toward delivering more infrastructure, more science equipment, more capability. This is not a colony. The word colony implies self-sufficiency, large populations, and political independence. Nothing being planned for the moon in the next several decades resembles a colony. What it resembles is a research station in Antarctica permanently staffed, regularly resupplied from the home continent, incrementally expanded as experience accumulates, and justified by the unique science and strategic value of its location. The comparison is not perfect, because Antarctica has breathable air and livable temperatures and wildlife and weather, all of which the moon lacks entirely. But the operational model is similar. A small, rotating crew, sustained by a logistics pipeline from Earth, gradually building the infrastructure and expertise needed to extend the duration and scope of operations. The South Pole strategy is not guaranteed to work. Water ice may prove too sparse or too deeply buried to extract economically. Equipment may fail in ways that cannot be anticipated. Dust contamination may degrade systems faster than they can be maintained. Radiation exposure may impose crew rotation schedules so short that continuous presence becomes impractical. The nuclear reactor may encounter problems that delay deployment beyond the current timeline. Any number of known and unknown challenges could slow the pace of development or force fundamental redesigns. But none of these potential setbacks disqualify the Moon as a destination. They simply reinforce what has been true throughout this entire story. The Moon is not easy. It was never going to be easy. The question was never whether the Moon is easy. The question is whether the Moon is possible. And the convergence of location advantage at the South Pole, potential ice resources even at modest concentrations, regolith as shielding material, near-continuous solar power supplemented by nuclear fission, pressurized mobility, and the proximity that enables iterative development. All of this taken together moves the answer from speculative to plausible. Plausible is not certain. Plausible is not guaranteed. But in the context of human expansion beyond Earth, plausible is extraordinary. Because when you compare the Moon's plausibility against every other destination humans have seriously considered for sustained presence, the contrast is stark. And that contrast reveals the final piece of the argument. The reason the Moon, despite everything terrible about it, may still be the first place humans truly learn to live in space. Mars has better marketing. That is the uncomfortable truth sitting at the center of every serious conversation about humanity's future in space. Mars has sunsets. Mars has seasons. Mars has ancient riverbeds carved into rust-colored terrain and polar caps that grow and shrink with the passing of Martian years. Mars has a 24-hour and 37-minute day that almost matches Earth's circadian rhythm. Mars has an atmosphere, thin as it is, that creates weather, dust storms and clouds. Mars has captivated human imagination since Giovanni Schiaparelli sketched what he believed were canals on its surface in 1877. Science fiction built civilizations there. Elon Musk built a company around getting there. The public conversation about humanity becoming a multiplanetary species almost always centers on Mars, as though the red planet were the obvious, perhaps the only, serious destination. But marketing is not engineering. Romance is not logistics. And when you strip away the mythology and compare Mars against the Moon using the criteria that actually determine whether humans can sustain a living presence somewhere, travel time, communication delay, resupply feasibility, rescue capability, resource accessibility, radiation environment, and current technological readiness, the comparison does not favor Mars. It does not even come close. Start with the journey. A crewed mission to Mars requires 6 to 9 months of transit each way using current or near-term chemical propulsion. That means astronauts spend 12 to 18 months of a roughly 30-month mission simply traveling through interplanetary space, exposed to galactic cosmic radiation, with no planetary magnetic field or atmosphere for shielding. The deep space radiation environment during transit is worse than the lunar surface because there is no regolith available for shielding and no terrain features to block particle flux from any direction. The spacecraft itself provides minimal protection. Studies based on measurements from NASA's Mars Science Laboratory cruise stage estimated that a round-trip Mars transit would expose astronauts to roughly 600 millisieverts of radiation from galactic cosmic rays, alone, not counting solar particle events. This exceeds NASA's current career exposure limits for many astronaut demographics. During transit, the crew lives in microgravity unless the spacecraft provides artificial gravity through rotation, a technology that has been conceptualized extensively but never implemented on a crewed vehicle. 6 to 9 months of microgravity produces the well-documented physiological deterioration observed on the International Space Station: bone density loss of 1 to 2% per month, muscle atrophy, cardiovascular deconditioning, vision changes from increased intracranial pressure, immune system suppression, and fluid redistribution. Astronauts arriving at Mars after 6 months of weightlessness would need to immediately function on a planetary surface with 38% Earth gravity, while their bodies are adapted to zero gravity. Studies of ISS crew members returning to Earth after 6-month missions show that many require assistance simply to walk. Mars crews would not have the luxury of medical support teams waiting at the landing site. The Moon eliminates this transit problem entirely. 3 days in microgravity produces negligible physiological effects. Astronauts arrive on the lunar surface in essentially the same physical condition they left Earth. No recovery period required. No transition from zero gravity to partial gravity. No 6-month accumulation of radiation dose during transit. The journey itself is a minor factor rather than a major risk. Now consider what happens once you arrive. Mars does offer some advantages that the Moon lacks. Its atmosphere, though only about 1% the density of Earth's at sea level, provides modest protection against micrometeorites, burning up smaller particles before they reach the surface. The atmosphere also enables aerobraking during arrival, reducing the propellant needed for landing. Mars has confirmed water ice in large quantities at its polar caps and in subsurface deposits at mid-latitudes, with some estimates suggesting ice sheets hundreds of meters thick covering areas larger than Texas. The Martian soil contains perchlorate salts that, while toxic to humans, could theoretically be processed to extract oxygen. The 24-hour day allows conventional solar power generation with a daily cycle similar to Earth's, though the greater distance from the Sun means solar panels on Mars receive only about 43% of the energy they would receive on Earth. These advantages are real. They are also insufficient to overcome the logistical barriers that proximity imposes. Water ice on Mars is abundant, but accessing it requires equipment that must be manufactured on Earth. Launched across interplanetary space, landed successfully on the Martian surface, and operated reliably for years without the possibility of rapid repair or replacement. If an ice extraction drill breaks on Mars, the replacement part takes 26 months to arrive at the next launch window, plus 6 to 9 months of transit. On the Moon, the same replacement arrives within weeks. The Martian atmosphere, while providing some benefits, also creates unique hazards. Global dust storms can blanket the planet for months, reducing solar power generation to a fraction of normal levels. The Mars Opportunity rover's mission effectively ended when a global dust storm in 2018 coated its solar panels and depleted its batteries beyond recovery. A crewed base dependent on solar power during a months-long dust storm faces a power crisis with no quick resupply option. Nuclear power mitigates this risk, but adds mass and complexity to a mission architecture that is already straining against every physical limit. The Martian radiation environment is better than deep space, but worse than the lunar surface in certain respects. Mars has no global magnetic field, so the surface receives galactic cosmic rays and solar particle events similar to the Moon. The atmosphere provides some additional shielding, reducing the surface dose by roughly 30 to 50% compared to the Moon, depending on atmospheric conditions. But this advantage is partially offset by secondary radiation produced when cosmic rays interact with the atmosphere, generating showers of secondary particles that reach the surface. The net radiation dose on Mars is lower than on the Moon, but not dramatically so, and still far exceeds safe long-term exposure limits without substantial shielding. The comparison extends to every operational dimension. Communication delay on Mars ranges from 6 to 44 minutes round trip, eliminating real-time Earth support. Launch windows to Mars open only every 26 months. Emergency evacuation from Mars is physically impossible within any useful time frame. Construction and infrastructure deployment on Mars must succeed on the first attempt, or wait years for corrective shipments. Every system must be designed for extreme reliability because maintenance support from Earth operates on geological timescales relative to human emergencies. The Moon is worse in some respects, less atmosphere, more extreme thermal cycling, harsher dust environment, lower gravity. But in every logistical and operational dimension, the Moon is dramatically more manageable. 3-day transit. 1.3-second communication delay, multiple monthly launch windows, emergency evacuation within a week, iterative construction with rapid resupply, real-time engineering support from Earth. These advantages do not make the Moon pleasant. They make it workable. What about destinations other than Mars? Free space habitats, rotating structures in orbit that generate artificial gravity through centripetal acceleration, have been proposed since Gerard O'Neill's influential work in the 1970s. These habitats could theoretically provide Earth-normal gravity, controlled atmospheric composition, adjustable lighting, and protection from radiation through structural shielding. In principle, they solve many of the problems that planetary surfaces present: no dust, no thermal cycling, no challenging terrain, customizable environments built to human specifications. The problem is that free space habitats require extraordinary amounts of material delivered to orbit. Building even a modest rotating habitat requires thousands of tons of structural material, atmospheric gases, water, soil for agriculture, and radiation shielding. Every gram of that material must either be launched from Earth at enormous cost or sourced from asteroids or the Moon using extraction and manufacturing capabilities that do not yet exist. O'Neill himself proposed mining lunar regolith and launching it to orbit using electromagnetic mass drivers, a concept that remains technically plausible but has never been demonstrated at any scale. Free space habitats are not impossible in the long run. They may eventually represent humanity's primary mode of space settlement, offering flexibility and comfort that no planetary surface can match. But they cannot be the first step. They require an industrial infrastructure in space that does not yet exist and cannot be built without prior experience operating on a planetary surface. The Moon, as the most accessible source of extraterrestrial material, would likely serve as the supply base for any future free space construction program. You cannot build O'Neill cylinders without first learning to mine and process material on the Moon or asteroids. The habitat comes after the mine, not before. Asteroids offer another theoretical destination. Near-Earth asteroids contain metals, water ice, and carbon compounds in varying concentrations. Some asteroids are believed to contain trillions of dollars worth of platinum group metals. Asteroid mining has attracted serious investment and engineering attention over the past decade. But asteroids are not places where humans can live. Most near-Earth asteroids are small, hundreds of meters to a few kilometers across. Their gravity is negligible, measured in thousandths of a percent of Earth's gravity. Standing on an asteroid's surface is functionally identical to floating in microgravity. Long-term human presence would require the same countermeasures against bone loss and muscle atrophy as living on the International Space Station. Asteroids have no atmosphere, no magnetic field, no thermal regulation, and no shelter beyond what is constructed artificially. They are resource targets, not habitation sites. More fundamentally, asteroids are far away. Most near-Earth asteroids require transit times of months to years depending on orbital geometry. Communication delays range from minutes to tens of minutes. Launch windows are infrequent and trajectory dependent. The logistics of sustained human presence on an asteroid face the same proximity barriers as Mars, without Mars's surface gravity, atmospheric shielding, or confirmed large-scale water resources. Every alternative to the Moon fails the proximity test. Mars is too far for iterative development. Free space habitats require an industrial base that does not yet exist. Asteroids are resource sites, not habitation platforms. The moons of Jupiter and Saturn Europa, Enceladus, Titan offer fascinating astrobiology targets, but lie so far from Earth that round-trip light-time communication delays stretch to hours and transit times to years. These destinations belong to a future century's exploration agenda, not this decade's habitation strategy. This process of elimination is not an argument by default, it is an argument by physics. The constraints that make the Moon the most realistic first destination are not arbitrary preferences or funding biases. They are consequences of orbital mechanics, the speed of light, human physiology, rocket propulsion chemistry, and the economics of mass delivery across gravitational potential wells. Any destination that requires years to reach, months to communicate with, and decades to resupply cannot support the iterative learning process that sustained habitation demands. Only the Moon offers the combination of proximity, resources, and challenge that matches human capability at this moment in technological history. But what does truly living in space actually mean? The title of this story makes a claim that demands precision. Truly living is not visiting. Apollo astronauts visited the Moon. They arrived, conducted operations measured in hours, and departed. Their stays were expeditions finite, planned, bounded by consumables packed before launch. Truly living is also not merely surviving. Astronauts on the International Space Station survive in space, but they occupy a laboratory in low Earth orbit, supplied continuously from below, rotated every 6 months, and incapable of existing without constant logistical support. Truly living implies something beyond both visiting and surviving. It implies duration that extends beyond individual mission timelines. It implies infrastructure that persists between crews. It implies capability that grows over time rather than remaining static. It implies the beginning of a relationship between humans and a place, not a one-night stay in a hotel, but the first months of residence in a home that is still under construction. The progression from visiting to living follows a pattern visible in every historical expansion into hostile environments. Antarctic exploration began with short summer expeditions. It progressed to winter overstays lasting a year. It matured into permanent research stations staffed year-round by rotating crews, supported by regular supply ships and aircraft. Today, Antarctica hosts roughly 1,000 to 5,000 people depending on season, living in heated facilities with greenhouses, medical clinics, recreation areas, and communications links to home. Nobody would call these stations self-sufficient. They depend entirely on supply chains from temperate nations, but they represent genuine, sustained human presence in a hostile environment. People live there. They work, cook meals, celebrate birthdays, argue with colleagues, shovel snow, repair generators, and conduct world-class science. The distinction between visiting Antarctica and living there is real, even if the living depends on logistical support from elsewhere. The same progression is beginning on the Moon, or more accurately, it is about to begin. Artemis 4, currently targeted for early 2028, will place astronauts on the lunar surface for the first time since 1972. Their stay will be measured in days a visit, not a residence. But unlike Apollo, the Artemis architecture is designed from the start to extend that stay incrementally. Artemis 5, targeted for late 2028, will begin constructing permanent surface infrastructure. Subsequent missions, planned at roughly annual intervals, will extend surface stays to weeks, then to months. Equipment left behind by departing crews will remain functional for arriving crews, accumulating into a base that grows with each mission. The transition from visiting to living will not happen in a single dramatic moment. There will be no ribbon-cutting ceremony marking the official establishment of a permanent lunar settlement. Instead, the transition will emerge gradually from a series of milestones. The first time a crew arrives to find a pressurized habitat already waiting. The first time oxygen extracted from regolith supplements the air supply. The first time a crew stays long enough to require resupply from Earth during their stay, rather than carrying everything from launch. The first time 2 crews overlap, with one arriving before the other departs. The first time a crew member spends 6 months on the surface. Each milestone represents a step along the continuum from visiting to living. This incremental approach is not glamorous. It does not make for dramatic headlines or cinematic trailers. It lacks the emotional punch of a single heroic mission planting a flag on Mars, but it is how sustainable presence actually develops in hostile environments, not through grand gestures but through accumulated capability, not through a single breakthrough but through 1,000 small improvements tested, validated, and refined over years. The real surprise of this entire story is not that the Moon is harsh. Everyone knows the Moon is harsh. The real surprise is that harshness may be a feature rather than a bug, The Moon's proximity to Earth means that every lesson learned on the lunar surface translates directly into knowledge applicable to harder destinations. Every life support system tested on the Moon generates performance data that improves the design of life support systems for Mars. Every radiation shielding strategy validated on the Moon informs strategies for deep space habitats. Every ISRU technique demonstrated on the Moon proves a concept that can be adapted for Martian or asteroidal resources. Every medical protocol developed for lunar crews extends the playbook for crews operating farther from Earth. The Moon is a classroom, a brutal, merciless, unforgiving classroom that offers no comfort and tolerates no incompetence, but a classroom nonetheless. And it is located close enough to home that students who make mistakes can survive them, learn from them, and try again. Mars does not offer that grace. A mistake on Mars may be fatal, and the lesson lost along with the crew that made it. On the Moon, the lesson survives because proximity ensures that failure is recoverable. This is not a comfortable conclusion. It offers no easy optimism about beautiful domed cities on the lunar surface or families raising children under Earthlight. Those images belong to a far future that depends on decades of engineering progress, institutional commitment, and political will that may or may not materialize. The near future of lunar habitation looks more like a research station than a city, a cluster of pressurized modules half buried under regolith, crewed by a handful of specialists, sustained by regular cargo shipments from Earth, slowly expanding as experience accumulates and technology improves. It is not romantic, but it is real. More real than any other option currently available to human civilization. And the realism derives not from the Moon being gentle, but from the Moon being close enough to reach in 3 days, close enough to communicate with in real time, close enough to resupply every month, close enough to evacuate in an emergency, close enough to build incrementally, fail safely, and learn continuously. The history of human civilization is a history of learning to survive in places that should have killed us. Humans evolved on the African savanna, adapted to temperate forests, crossed deserts, scaled mountains, settled Arctic coastlines, built platforms on ocean surfaces, and established research stations on the most isolated continent on Earth. None of these environments were welcoming. None of them invited human habitation. Humans went there anyway, driven by curiosity, competition, necessity, or sheer stubbornness. And they learned to survive through the same process that the Moon now demands: iterative adaptation, incremental improvement, accumulated knowledge, and the stubborn refusal to accept that hostile means impossible. The Moon is the next environment on that list. Not because it is the easiest. It is the hardest place humans have ever seriously attempted to inhabit. Not because it offers the most reward. The scientific and strategic returns of lunar presence, while significant, do not compare to the potential bounty of Martian resources or asteroidal minerals over the very long term. The Moon is next because it is the first place beyond Earth where the iterative process of learning to live can actually function, where failure is survivable, where lessons can be applied before they are forgotten, where supply lines are short enough to sustain a growing presence through the inevitable setbacks that accompany any expansion into hostile territory. Right now, as you listen to these words, 4 astronauts are swinging around the Moon aboard Artemis 2, testing the spacecraft that will eventually carry crews to the surface. Within 2 years, if current schedules hold, astronauts will stand on the lunar South Pole for the first time, looking out across terrain no human has ever touched, surrounded by vacuum, bombarded by radiation, stepping on dust that could shred their lungs, and beginning the work of learning to stay. Not forever, not comfortably, but for longer than anyone has stayed before, and then longer still. The Moon will not welcome them. It will try to kill them in every way: a world without air, without water, without warmth, and without mercy can try. And they will survive, not because the Moon relented, but because Earth is close enough to help, close enough to send supplies, close enough to hear their voices, close enough to bring them home when the stay is done, and send them back again when the next mission is ready. Humanity's first real home in space will not be a paradise discovered. It will be a fortress built, piece by piece, on the most hostile ground within reach, by people who understood that the question was never whether the moon is dangerous. The question was always whether it is close enough to learn on, and the answer, confirmed by orbital mechanics and validated by 50 years of spaceflight experience, is yes. Barely. Grudgingly. Unsentimentally, yes. The moon is terrifying, and it may be the first place humans truly learn to live beyond the world that made them, not because it offered comfort, but because everything else was even harder. That is not a story of hope finding a gentle shore. It is a story of survival choosing the least impossible option and building something extraordinary from it. The first home beyond Earth will be earned in dust and radiation and silence, constructed by people who knew exactly how dangerous their new world was, and went anyway, because the alternative was never going at all.